All right, welcome to Math 408, L functions and sphere packing. This is lecture 10. And so we're going to continue our talk on interpolation. And then we're going to go from that to some Fourier analysis because we need some results from Fourier analysis for some of the theorems we're going to prove. If you haven't seen Fourier analysis before, it's a beautiful theory, a lot of wonderful things you can do. So we've talked about interpolating where you know either values at points or values at points and values of derivatives. And if you want to find a polynomial, in some sense we've seen it's really not that hard. You give me enough points and we will get the polynomial. Not every function in life is a polynomial. So the question becomes, well, what if I have a function that isn't a polynomial? How well can I approximate it? And why might I care about this? So one of the reasons you might care sending images. Did we talk earlier about how you could hide a message in a message? You don't want to send every single pixel, because if you send every single pixel, that's expensive. What you want to do is you want to send a few key values that allow you to recapture the image that you receive. So it's important to remember when you're streaming video, what do you typically stream video on? So I'm expecting several different answers. What do you stream video on? I'm not even asking, do you stream video? I'm just assuming you all stream video at some point. YouTube. Okay, but how do you stream it? What do you use?
My computer.
You use your computer.
A phone.
A phone. Maybe a laptop. You're not using extremely old technology. You have a device that has decent processing power, that has storage abilities. So when you are transmitting, you can actually use the fact that you have a local device that can do a decent amount of computation. So in calculus, you learn about Taylor series. And if you have a few key Taylor coefficients, you can approximate the function very well. So we want to generalize this to higher dimensions. And so Taylor series is one-dimensional. Maybe we want a two-dimensional Taylor series, and we have one for red, one for green, one for blue, and we send those triples. And so we would send 3 different Taylor coefficients for an image. And that would be a lot less data to send. And then, of course, you have to be a little bit careful. If you're looking at this from your seats, the color changes remarkably from here to here, or from here to the floor. And you will have points of discontinuity. And that can affect then how you transmit. When you have given functions, what can you say about the resulting Taylor series? Taylor series are nice to use. They give you finite polynomials, but there may be better polynomials to use, or there may be better functions to use than the 1x squared. And there's a very deep, rich theory in mathematics about different bases that you can use. You can have bases for functions. We will do a lot with the sines and the cosines, or essentially the same thing with the exponential function, because e to the I theta is cosine theta plus I sine theta. Or if you have a really old math book, they sometimes do this, cosine I sine theta. And the idea is, if you have a nice image, sending a few pieces of data is all that you need to do. You don't have to send every pixel. All right, so if we're going to do this, it's not enough to just interpolate polynomials. We have to interpolate more general functions. And so here is a question. We'll make this homework. So given, say, x0, y0, dot, 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 xn, yn, where, let's say, xk is k over n, and yk is f of xk. how do you estimate f of x? So this is the most general problem I can give you. You know, I'm just restricting things to the unit interval to make things nice for myself. If I was doing a trig function, rather than doing k over n, I might do k over n times 2 pi, or k over n times pi over 4, something like that. And so how would you do this? What would you choose? And so I'm going to leave this as a homework question. There's more than one answer. And then, of course, you might ask, well, what information am I allowed to use? So what if you have more info? What would you like to know? So we'll make that question 1, we'll make that question 2. Question 3, we'll do the function f of x equals e to the x. F of x equals the log of 1 plus x. And we'll do f of x equals cosine of x with xk equals, say, k over n times pi over 2. Because if we can do cosine up to pi over 2, we can do it in greater generality. So just think about how you might try to estimate, to interpolate in these places. And it's okay if you have, here's my first crude, really stupid thing. Here's something that's a little bit more clever. All right. Any questions on the assignment? Okay, so last time we actually were able to get essentially the formula that my colleague wanted us to get. We saw we were able to generalize from the line. And one thing I loved about the conversation we had was that it wasn't clear initially how should we view the line. And so much of algebra is trying to figure out what is the right way to view things. Okay, now what we want to do is we want to look at things a little bit more generally. And so we're going to need to do Fourier series. So I know some of you have seen Fourier series before. How many of you have not seen Fourier series? Okay. It's not a requirement for the class, so I am not expecting people to have seen Fourier series. Let's do Taylor series. And it's all homework due Monday, October 12th, 11:59 p.m. And I believe that there is no class on Monday. It is reading period.
Yeah. What?
Yes.
Is reading period on Tuesday too?
Yes, reading period is on Monday and Tuesday. Some people are doing War and Peace and they need 2 days. All right. So Taylor series. So the nth Taylor series of f, and you might want to write this maybe f sub n of x. Either one of these is fine notation. Is going to be a sum. K goes from 0 to n. The kth derivative. And I'm doing the Taylor series at the origin over k factorial times x to the k. If you think about it, this is in some sense a wonderful thing to look at. Imagine I can only give you one piece of information about the function at time 0. That's it. If I can only give you one piece of information, what would you like to know? Its value. So we start off with f of 0. And so the 0th Taylor series expansion is just a straight line. So let's say f of 0 is 8. I almost said 5, but 5 is a bad number to write on the board because it could look like an S. So let's say you know that at time 0, you are 8 miles from home. Where do you think you are 1 hour later?
8 miles.
8 miles from home. That's your best guess. I have no idea. Am I moving towards home, away from home? Am I going in a circle around home? If all I tell you is that at time 0, your value is 8, your best guess for all eternity is that you are always 8 miles from home. Well, this is a 400 level class. I should give you a little bit more information than that. So I will give you one additional piece of information. What would you like to know? Well, I could give you that. How fast you're moving. So those are two equivalent things. If I tell you where you are 1 hour later, you can then use that to get your average speed in that interval of time. Or keeping all things local, maybe f prime of 0 is 40. Here, let's make it even higher. Make it 400. Right? So you are traveling 400 miles an hour. What's your best guess as to where you are 1 hour later? 408. And so what we would now do is we would now have our best fit straight line. And so this leads to T0f of x is just 8. This leads to T1f of x is 8 plus 40 x, 400x. And then if you could have one more piece of information after this, what would you choose?
Am I speeding up?
You're right, you would ask for your acceleration. Given that f prime of 0 is 400, I might ask for the location of the cops, but we'll take acceleration. And if I tell you that the second derivative is 0, then that means you're accelerating. And this will lead to the best fit polynomial. So this would be a quartic. Oh, sorry, quadratic. So you get T2f of x is 8 plus 40x plus 2. Actually, let's make this 21. 21 x squared over 2 factorial. And the reason I want to do this is I don't want the 2's to cancel. The reason we have the factorials here is if I take the value at x equals 0, I get 8. Beautiful. If I take the first derivative, the 8 vanishes, and I'll just get 40, which at time 0 is exactly what I have here. Great. If I take the second derivative, the 2 factorial cancels the 2 factorial down here. And so we're choosing these Taylor polynomials so that we match derivatives. So if I have a polynomial of degree n, matches up to the nth derivative at x equals 0. And the hope is the more derivatives you have, the better job you do and the longer region you can go where it's still going to do a good job. Okay? This does not necessarily mean that this is the best fit polynomial of degree n. Because you could ask, well, how do we measure what we mean by best fit? Maybe we have an interval and we look at maybe the integral of the absolute value of the difference. And we want that to be as small as possible. Or maybe we look at the integral of the absolute value squared. And we want that to be as small as possible. This is going to make things great in terms of matching the derivatives, but maybe some shit happens a little bit away from 0, and this is not going to notice that. And so it might be better to actually have something that does a worse job at 0 to do a better job later. But if you're looking at what's going on very close to 0, this should be a very good way of proceeding. All right. Everybody should have done Taylor series. What questions can you ask about a Taylor series?
How good is it?
How good is it? What else?
Is T infinity about f?
Good. Does T infinity of f equal f? Your question, however, presupposes another question.
Oh, is f continuous?
Like, for what function is f does this work on, maybe?
What do you mean by does this work on?
Like, because there might be some functions where, I guess, basically we're assuming that it's like differentiable to a certain degree for this to work.
Right, so in fact, the function needs to be infinitely differentiable.
Does Tn converge?
Does Tn converge? Right, the very first question you should ask whenever you have an object, does it converge? So anytime you see an infinity, this is a danger sign. We don't know that Tnf converges. If it converges, then the natural question to ask is, does it converge to f? There's a related question that you should always ask when you ask about existence.
Is it unique?
Is it unique? What do you mean by is it unique?
Is this like a unique sequence of polynomials which converges in some sense?
So is there a unique Taylor series associated to each function? That is different than could two infinite sums be associated to the same function? I'm sorry.
Is it?
Oh, I think I want to phrase this. If I give you a Taylor series, could the Taylor series correspond to multiple functions? So can two different functions have the same Taylor series? So out of curiosity, have you seen questions like this when you've done Taylor series? Okay, what is the answer to convergence? Always?
No, on a given radius. Yeah, it depends. What's the radius for?
So the convergence is going to depend on how fast the derivatives are growing. And because k factorial is growing very rapidly, k factorial is approximately k to the k e to the minus k square root of 2 pi k, which is basically, k divided by e to the k square root of 2 pi k. This is growing extremely rapidly. So as long as your derivatives are not growing tremendously fast, you're in good shape. But there are some functions you need to be very careful about. And so if I give you the function g of x is e to the negative 1 over x squared if x is not 0, and 0 if x is 0. This is one of my favorite functions, because this function shows you just how horrible the theory is. So it's a nice exercise to prove that every derivative of g at 0 is 0. And the hint is L'Hopital it. You've made it when your name becomes a verb. Okay? As a nice exercise, I'll just put this as recommended. You don't need to do this, you don't need to write it up, but you should be able to do this calculation and show that all of the derivatives at 0 are 0. But the function is not identically 0. If you plot it, it's going to be incredibly dead towards 0. If you put in x equals 1 over 100, you have e to the negative 100 squared. If you put in x equals 1 over a million, you have e to the negative a million squared. It is crunched down to 0 fast. But it's not identically 0. So out of curiosity, I know I do this in almost every class I teach. I try to work it in. How many of you have not seen this function before? Good, so everybody has seen this function before. This is the typical example of how bad things are. as a brief aside, because I know some of you are either taking complex now or have taken it in the past, this function also shows you why complex analysis is so much better than real analysis. Real analysis is the elitist country club that will only I'm sorry. I think it's the other way around. Complex analysis is the elitist country club of mathematics, where only certain functions are allowed to be considered differentiable. Real analysis is the very democratic, sure, come on in, more the merrier. For the most part, that's a good philosophy to have. When you are extremely specific about which functions you are looking at, they often have additional properties, and those additional properties are nice. So if you're going to do Taylor series, what must be true about the function if you want to calculate its Taylor series? Infinitely differentiable. Before it's infinitely differentiable, what's the weakest statement? It must be at least... Okay, and even weaker than it must be differentiable. Weaker than that, it must be... Right, if it's not even continuous, game over. If we look at g of z is e to the negative 1 over z squared, if z is not 0, and 0 if z equals 0, well, we already know if we take z to be real, the function is going to 0. If we take z to be, say, I over n, with n going to infinity, g of I over n becomes e to the negative 1 over z squared. The I squared cancels the negative 1. The 1 over n comes upstairs, and you get e to the n squared, which is going to infinity. This function isn't even continuous. So we would never even try to do a Taylor series expansion of this in the complex plane, because it's not even continuous. The truly remarkable fact about complex differentiable functions is if you're differentiable once, you're differentiable infinitely many times, and you equal your own Taylor series expansion. And in complex analysis, they have two words. Holomorphic means differentiable. Analytic means you equal your series expansion. And eventually you have a theorem that says these two words are actually the same. It's not the case in real analysis. Because this function has a Taylor series that's identically 0, I can add this to any function I want. You know, if I give you 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, what function am I thinking of? You might think I'm thinking of cosine, but I'm actually thinking of cosine of x minus 1,701 g of x. Because 1701 is such a beautiful number. There's no way you could tell that. And there's so many issues that come up because of this that makes analysis very hard. Real analysis is a tremendously challenging subject. Complex analysis is much nicer. Because basically, all the problem functions of real analysis are forbidden entry. Okay, any questions on Taylor series? So here we're basically using the functions 1, x squared, x cubed, x to the 4th. And the hope is that maybe we can use better functions and get other results. Out of curiosity, how many of you have seen the Vayastras approximation theorem?
I feel like I've heard of it.
That any continuous function can be approximated by polynomials? And you can generalize this a little bit more. All right. Maybe we'll have some comment about that later. There's lots of different ways of proving that result. Okay. So what I want to do now is, instead of using Taylor series, I want to use trigonometric series. So a little personal history. I had two thesis advisors, Peter Sarnak at Princeton and Henrik Ivanitz at Rutgers. Peter Sarnak was a student of Paul Cohen. Anybody know who Paul Cohen was?
One of the Cohen brothers.
No. If you think back to the Cantor problem about the cardinality of sets, the continuum hypothesis, is there a set of cardinality strictly larger than the rationals and strictly smaller than the reals, the continuum. What Paul Cohen proved is this is actually independent of the other axioms of set theory. You can take it or leave it if you want. His advisor was Zygmunt, who was extremely famous for, among other things, writing a terrific textbook or volume on trigonometric series. I think it might have even had 3 volumes. Just a truly wonderful classical subject. This goes back in the 1800s. It was really pushed initially by a lot of people doing natural science and trying to solve differential equations related to heat flow and other problems like that. And they found, not surprisingly, that trigonometric sums do a wonderful job, and that's a convenient way. To some extent, do you really need to do trigonometric sums, or could you do things with polynomials? So a trigonometric sum might be, the sum, n goes from minus n to n of, say, an e to the 2 pi I and x. And if I write it like that, this is the same as a function of sines and cosines. Because I can expand each of these out in terms of a sine and cosine. And I hope you see that I can go back and forth between the two. I can write things in terms of the exponential, or I can write things in terms of sines and cosines. And the key is that, cosine of x is e to the ix minus e to the minus ix over 2. And sine of x, it's plus x, is e to the ix minus e to the minus ix over 2i. So I can go back and forth between sines and cosines and exponentials. But I'm claiming something stronger. That I can go back and forth between sines and cosines, and I Taylor series in functions 1x squared. How could I do that? Yes, sine and cosine have Taylor series. So basically, Taylor expand. And then this has to be made rigorous. But this is one way to prove the Vayastras approximation theorem, that you can approximate a function, a continuous function arbitrarily well by a polynomial. Well, you approximate it arbitrarily well to a higher degree with sines and cosines. Then you expand the sines and cosines, is because you only have a finite sum. If you go far enough along, things are going to decay. They're not going to really change anything. And then each one of these you expand out in terms of sines and cosines. So a lot of this, not surprisingly, just comes down to which is going to be the most convenient form for the calculations we need to do. It's frequently nicer to be working with sines and cosines than with the 1x squared. Have you all talked about orthogonality and between functions? That if I give you 2 functions, f and g real valued, we would say like the inner product of f and g would be the integral, let's go from 0 to 1, of f of x g of x dx. And if the functions were complex valued, it would be f of x times the complex conjugate of g. All right, so everyone has seen this. Do you know why we use this as the definition of inner product? So this is one of the things that is always a challenge. I know you've seen a lot of these results, but I'm not sure if you've seen why we use them. So why are we using this to measure? Have you seen any justification for this? Or did your textbooks say, well, this is how we're going to define the angle between 2 functions? So we slipped it by you. You never questioned, why are we doing it this way?
I feel like they might have told me.
They might have. Which is possible. So then I'm asking you now, is this a reasonable definition? What properties would you want this to have?
F of G, or F dot G equals to D dot.
Good. So f dot g equals g dot f. We have that. What else would you like?
F of g plus h, or f dot g plus h.
So distributive.
Linear more broadly.
So more broadly linear. Good. So af1 plus bf2 dotted with c1 g1 plus c2 g2 equals, just write check. What else? Basic property that you're missing, yes.
F dot f.
Okay, f dot f.
Magnitude of f, I don't know what that means.
Is the magnitude of f, or squared. And what should be true about the magnitude of f?
Positive.
Almost.
Non-negative.
Non-negative. And is 0 if and only if, and I'll put f equals 0 in quotes. So what does it mean for a function to be 0? If I have a function that's 0 everywhere, but at 1/2 it equals 1,000. Well, if I do any integrals against that, the integral will still come back as 0. So how many of you have done measure theory?
Right now.
Okay, right now. Great. So I'm going to just focus on you. So when you're doing measure theory, there's a nice way to talk about what this means.
It's zero. It's non-zero on a set of measure 0.
It's non-zero on a set of measure 0. Exactly. So these would be wonderful properties to have, and you can show that they all exist. So here's a way to try to justify the definition. Let's say I give you a function f of x, and I'm going to associate to that the following vector. F of 0 over n, f of 1 over n, f of n over n. And if I take another vector, g of x, I'm lazy, so I'll just put like quotes over there and do the same thing for g. And now if I look at f dot g, this is like the sum of f of k over n, g of k over n. K goes from 0 to, let's say, n minus, well, maybe go up to n minus 1. Do you like this?
I think it's the same issue. I mean, like, there's so many ways you could define them in the product.
Yes.
That, like, you're just choosing the multiple of.
I'm basically trying to say, look, if I have a function f, I'm looking at it as like a tuple in an n-dimensional vector space. And I know how to do dot products in n-dimensional vector spaces. I just multiply them component-wise and add. Do you like this? Or do you mostly like this and you would like it more if I just did a small little favor? I'm sorry?
I don't like the sum.
Okay, so you would love to say, come on, prof, let n go to infinity and have this become an integral.
Yeah.
What would happen if I let n go to infinity right now? Give me a good function to test things on. Give me a good function for f. F should be 1, and g should be
1.
So if f equals g equals 1, then what does this become? It becomes n, which is going to infinity. The sum is exploding. We want the norm of f to be its length. What should the norm of the function that's identically 1 be? It should be 1. Can you save this definition? How do you save it? Yeah, you put a 1 over n here. And if you put the 1 over n here, now, if you take the limit as n goes to infinity, now you get the integral from 0 to 1 of f of x, g of x dx. So this is where the definition comes from. It comes from approximating what we have as a vector in n-dimensional space. And letting the dimension get larger and larger and larger, we're going to capture more and more pieces of information about the function. But we need to put in this factor of 1 over n. And when we do that, then things will be nice in the limit.
How important are the bounds that we chose? Like,
Not at all.
we could have done one.
Absolutely.
two, or-
And we could have done it from a to b, we could have done it from minus infinity to infinity. If we do it from minus infinity to infinity, then we have to be a little bit more careful. Now we have to talk about our functions have to maybe decay. And so it is convenient when you have things defined on finite intervals. Okay. So now that we have a definition, we can look at what we're going to consider our key functions. So the key functions it's either the set e to the 2 pi I and x, or sine 2 pi nx cosine 2 pi nx. There's advantages and disadvantages to both. How many people have completed a class in complex analysis? Okay, so no hands have gone up. So using e to the 2 pi I n x might be a little bit problematic because we're now going to be integrating functions with a complex variable. So sines and cosines might be more convenient. But the complex notation is very nice. Complex analysis is a beautiful subject that maybe it's worth the pain of just talking about what this means. And so if I want to find the integral from, say, a to b of f of x e to the 2 pi I n x dx, by this I just mean the integral from a to b of f of x cosine 2 pi n x dx plus I integral from a to b f of x sine 2 pi nx dx. So if I use the complex notation, that's just equivalent to saying I want to do this. It turns out for the problems we consider, normally we don't want to have f of x times e to the 2 pi I n x. We want to have it times the minus, the negative of that. Well, cosine of input and negative input are the same. Sine of input and sine of negative input differ by a minus sign. So all that means is I replace this with a minus sign. Why do you think I want to do f of x with e to the negative 2 pi I n x, not f of x with e to the 2 pi I n x?
One gets really big.
Well, they're the same.
Oh,
They're the complex conjugates of each other. What will f dot g be for complex functions? So the integral from 0 to 1 of f of x times what? Times the complex conjugate of g dx. So if I'm taking the dot product of two complex valued functions, I have to remember that I take the complex conjugate here. And so what we're doing here is this is really the dot product of f with e to the 2 pi I and x. That's why we like to have a minus sign there. As an aside, let's do some linear algebra. No. No, I think I was right the first time. So let's take the matrix 0, negative 1, 1, 0. What does this do? Rotate by how much? 90. And we've already talked about the fights that mathematicians and physicists have in terms of how we do spherical coordinates. It turns out that we have other heated conversations at times. You know, are you rotating the point or are you rotating the coordinate axis? And sometimes the two fields have slightly different notation for a rotation. If you take A of 1, 0, that's a point, you know, just 1 unit down on the x-axis, that moves this to 0, 1. So that's moved at 90 degrees. If I take A of 1, 0, observe 0, 1, then I'm going to rotate it 90 degrees. I'll get I'll get negative 1, 0. So since it rotates the two basis vectors that start off at 90 degrees by 90 degrees, it rotates everything by 90 degrees by linearity. Can you give me an eigenvector for this matrix? So, you know, solve A of v equals lambda v with v not being the zero vector.
No.
Why not?
The eigenvalues are complex.
The eigenvalues are complex.
I can't give a real vector.
I'm sorry?
I can't give a real vector.
Ah, good, you can't give a real vector. So the eigenvalues, lambda equals plus or minus I. If you try v equals 1 comma I, then AV is going to be minus I, and then it's going to be 1. And that's the same as minus I times the initial vector. So 1I is an eigenvector with eigenvalue negative I. Why do I care about this? Sadly, I'm a little bit short on space, so I'll just write it up over here. If I do 1I and do the standard dot product with 1I, the way you would do the standard dot product is you would do the sum of the squares, component by component. So you would get 1 squared plus I squared, which is 0. So if we just do the standard real dot product, we've just said that the vector 1I has no length. It has a length. That's why we do the complex conjugate. So again, all we're doing right now is motivating a lot of the choices we're going to be making as we go through trigonometric series and Fourier analysis to get to formulas. There are 3 acceptable ways to define the Fourier transform. When I was taking my exam, I was asked by my advisor, or my soon-to-be advisor, how do I define the Fourier transform? I knew which definition to give. Depending on which problem you're doing, certain versions are more useful than others. And so, one of the things we're going to need is one of the most beautiful formulas in all of mathematics. So how many of you have seen the Poisson summation formula? Have you seen a proof?
Yes, but I cannot produce one.
Okay. So let's say f is good. It is a technical term that we will define as we go further. Then the Fourier transform is going to be f hat of y is equal from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. What is the first thing you want to ask about the Fourier transform? Does it exist, right? First question is always, does it exist? If the answer is no, not worth studying. There is a joke about somebody who, in their thesis they proved certain functions which satisfy a collection of technical properties have certain properties themselves. And then according to the story, a few years after they published their thesis, somebody proved that the only functions satisfying these conditions are the constant functions. And most of these results have long been known about constant functions. For instance, constant functions are infinitely differentiable. Yeah. These are not impressive results. You want to know what space are we looking at. So the first question is, what do we need for the Fourier transform to even exist? Well, f hat of y in absolute value is less than or equal to the integral from minus infinity to infinity of the absolute value of f of x dx, because this has absolute value 1. It's cosine plus I sine. Has everybody heard of the space L1? Functions whose absolute value is finite when you integrate. Okay, so L1 of an interval I is the set of all f such that the integral over I of the absolute value of f dx is less than infinity. What do you think L2 would be?
The integral squared.
Yeah, the integral squared. And so more generally, LR, I would just raise that to the nth power. And so the key spaces that we often look at are L1 and L2, functions that are either integrable or square integrable. And so here, if f is integrable, that is enough to imply that the Fourier transform exists. And the beautiful result is that the sum n goes from minus infinity to infinity of f of n is the same as the sum n goes from minus infinity to infinity of f hat of n. Now the question is always, who gives us, why would we care about a formula like this? Well, we're replacing one infinite sum with another. The hope is that maybe this function is slowly decaying. So we need to evaluate a lot of terms to have a really good, accurate assessment of this value. But maybe f hat is rapidly decaying. So rapidly, in fact, that this is essentially f hat of 0 plus really, really, really small. And if that's the case, then we can get an incredibly good estimate of this by just looking at one term. I can sum one term. That's not so bad. So for Wednesday, what is f hat of n if f of x is 1 over square root of 2 pi e to the negative x squared over 2? Why might I be choosing this function?
Who doesn't like the normal?
Who doesn't like the normal? You might even say you'd be abnormal if you don't like the normal. Right? It's a wonderful function. It's an incredibly important function. But maybe that function is not quite the right thing to study. Maybe I want more generally maybe f sigma of x is 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared. I'm not bothering to put in the mean. The mean is not a big deal. The hope is that if you understand a function, you might understand a rescale like this without too much trouble. The 1 over square root of 2 pi sigma squared, well, that's just a constant factor. That's not so big of a deal. You could write this part here as e to the negative x over sigma squared over 2. And so the question becomes, if I have f, and f goes to f hat, and I have, say, g of x is f of ax, then what is g hat in terms of f and a? And there should be a nice formula for that. So for the next class, we'll talk a little bit more about what we need to prove Poisson summation. I'll give some applications either in the next class or the class after that on why we care about Poisson summation. but it's going to allow us to evaluate a lot of sums, or if we can't evaluate them, to at least approximate them. And this is, sadly, one of the big themes, is that most problems we can't solve exactly, but if we can approximate things, frequently in the limit, it's enough to just be able to approximate. And for a lot of things that in the limit, all the really, really, really small actually goes to 0. And it just converges to f of 0, or f hat of 0, which is wonderfully nice. All right, so this is a good place to